Okay, let's start the third day of the lunch. Did you enjoy the last evening in Osaka? Right. Today we will begin with Alastair Butler, the semantic representation. Many of you would know his approach, and this is the newest his theory. So please.
His lonely approach. Okay, so today I'm going to be talking about dot-to-dot semantic representation. So it's really just talking about representation. It's not really about how we get to semantic representation. I'm assuming that. Screen is this. Oh, screen is that. This is a different screen. Yes. Oh, I want to show all of it. Yeah. No. This is going to be a nightmare. Oh, so I have to be what? Each time? Yes. Push the button. No, but oh, I see. So, but each time I change application, or
You should change the
to desktop. Yeah, I'd like to show my desktop. Yeah.
So let's restart. So it's not connected.
Yeah, but I want to show stuff on a local server that's running on my computer. Okay, just we have to do this.
真ん中のやつでいかないと多分。
これにしたら全画面になる。でもそうすると、今のこれで。
Yeah, this is looking right. Yeah. This is great. Thank you so much. Okay, so I basically gonna get on. Yeah. Okay, so okay, so today I'm going to be talking about dot-to-dot semantic representation, which is a representation of semantic information. I'm not going to be talking so much about how the actual representation is built. That I've kind of written about quite extensively before. So you might check out the references or whatever. But you'll get an idea anyway. So what is this representation? Well, first of all, my goals of the talk. So I want to introduce the so this is an encoding of abstract dependency interpretations of natural language data. And it's pitched at a level of abstraction that I want to be informative about semantic argument dependencies and scope relations across discourse. So this is really the kind of goal to represent this information. But I still want to be able to recover the language data. This is actually very important for me because I want to be able to easily get back to the language data to know that these representations are really valid. So this is a kind of crucial consideration. I must be able to understand my pictures. Otherwise, what are they showing? Okay, so it's rather like the SEMR representation of meaning text theory by Mel Cook. I don't know whether you guys are familiar with this, but it's very brilliant work. And a more modern or popular link is with abstract meaning representation. So what is a link? Well, so all of these things are event semantic relation based. So actually, we've seen a lot of event semantic relation-based work already. And this kind of stuff is very easily visualized as graphs. That's kind of the most attractive feature is that you can really easily read these graphs, which is yeah, more attractive than a formula. And you can use them for knowledge representation purposes, which is useful. Wrong computer. But there are some points of difference. So one point of difference is I'll have connections across discourse, which is kind of important. And there's going to be representations of scope and quantification. The previous things I spoke about, the SEMAR representation and the AMR, they don't represent any scope information. They're sentence-based. So this is quite different. There's also a text-based rendering that you'll see. And there's also, in a sense, less abstraction because the original language is recoverable. Okay, so my background assumptions are basically semantics revolving around discourse entities. We've seen lots of talks already that are very supportive of this outlook, and DRT and dynamic semantics are two possibly, two flavors of that, kind of realizing that vision. Yeah, okay, so how can we picture information from discourse with a graph? Well, that's what we're going to be doing. So each node of the graph is a discourse entity. And the connections leading to or from the nodes, this is gathering the information content that's communicated by the language data. And the language data can be a sentence fragment or a sentence or indeed a full discourse. So here's a simple example. He has a story to tell. So here we've got a graph with 4 nodes, and we've got some connections happening between these nodes, which are kind of capturing the argument relationship, and consequently we're capturing the semantic content. He is just being, so basically you reference the word. This he is an unresolved pronoun here, so it's just occurring as an unresolved pronoun, a discourse entity that presumably is going to be linked in some way to something else. And we've got these argument information. So arg0 is basically the subject or agent of the having, and arg1 is the object or the thing had. It should be reasonably easy to see that this is representing this information. We've also got the information here that the story was told, yeah, but we don't have a teller information here, yeah. It could be that the he is doing the telling, but that's not what that sentence says. So we haven't got a link between the he and the tell here. Okay, so that's the general look of these representations. They're super easy to read, and that's the attractive feature. And they encode the information. So how does this pan out for? Well, this is very inconvenient. Well, it's possible to move this somewhere else. Maybe we can move it up here. Yes. So this is an example with a bit more content. He must have to tell the story to every conference attendee. So here we've got some scopal operators, must, and a quantification of every. And we've got information here that this is the scope of the every, and this is the restriction. So I hope you should be able to see that this is capturing basically the standard predicate logic rendering of this kind of sentence. And then we need to go to worry about discourse, connecting these guys together. So he has a story to tell. He must have to tell the story. So this is the merging together of these two sentences. And here we've got anaphoric resolution happening. So here is our he has a story to tell. And then we've got the he must have to tell the story, where the telling of the second sentence, the the numbers here are indicating the number of number within the position of the word in the sentence position. So this is the fifth word of the second sentence, and this tell is happens to link back to he is the subject, and the definite, the story is linking back to the story that we introduced with our indefinite here. So this is capturing the discourse connections, and it's representing our quantification in a way that can be nicely transformed into easily interpretable structure. Okay, so yeah, so yeah, so now I want to actually show you this this is implemented, and it's implemented at quite a scale, because I've been kind of annotating corpora for a while now, and in particular, oh gosh, lots of corpora here, but let's look at the English one. So this is a corpus of, I don't know, 500,000 words, so it's a reasonable sized corpus, not massive, but a reasonable size. And this is got syntactic trees. Oh, I did have an example. 65. Here we are. So I mean, this is real life data. So this is this is the reality. This is not John Smythe's. And this is what you have to contend with. Let's make it. So we kind of build up a tree structure that represents the kind of syntactic information, and then we want to convert this thing into semantic representation. And that part I'm not telling you about. What I'm going to do is I click on this button, and it will do it for me. So that's a real-time transformation that's just happened. That's not a canned result. That's happened from the tree. And you can see we've got like lots of dependencies happening here. We've got the subject, which is our I here, and this is what typically happens in English. You introduce your subject, and it permeates down all the way down through the structure. It's I, linking, and that's exactly what we have. That's exactly what we have in this structure. Everything is linking around. So this is what dependency graphs should look like. If your dependency graphs don't look crazy with lots and lots of connections, they're wrong. And kind of, but this is like, how do we make sense of this? This is like a mess. And we want to zoom in on particular parts. So here's a zoom. Yes. So here I picked out a picture of my tree. So John Adams asked me to continue this the 100th. So this is kind of interesting. We have a control relationship happening here with some control relationship already, and you conveniently mark with orange mark. We can zoom in we can look at the just that's convenient here, and the relationship. John Adams asked this, continue. This here is this in the original sentence here has this. So this is the noun is the head. The head noun is missing. So that's why we've got this kind of dummy index thing. We've got another with parenthetic because this is contribute and issue. That issue is missing. 100. The issue of 100 issue is also missing. So good. So these are the kind of representations that I can that this system is generating, and that gives immense fun because I can play around with all the stuff. And oh, how am I doing for time? Oh, I had quite a good time. Oh well, not that much. It's 17 minutes. Okay, so where were we? Ah, yes. So this is very useful for extracting information. So say I've got a story, yes, like Peter Rabbit, because that's a story that most people know, and this one that I've obsessively annotated. We can do the same trick where we collect together all the facts from Peter Rabbit, and that's kind of what's happened in this this file here. So these are all the facts extracted from Peter Rabbit. So all the various things that a rabbit did. And now we can query these things because these are just as written here. These are data log entries. So now we can ask what happened to Peter if you're really that interested. And here's well, that's too specific. Oh, wrong data set. So here, this is all the things that happened to Peter Rabbit in Peter Rabbit. If you like really want to enter any quiz. So you see, Peter Rabbit is like in the center because everything is linking around Peter Rabbit. How do I scroll across? So these are all the various things he did. He was most dreadfully frightened, Mr. McGregor, doubtless, and he was in the garden. And oh, here we got top of Peter. Oh, but no more connections because we kind of bottomed out for how I'm collecting connections. So I'm kind of interested. Well, what happened to the top of Peter? His head. It's a crucial question. If you're a Peter Rabbit fan. So let's ask about the top of Peter. It's probably enough for me to just put top here. So this is what happened to the top of Peter. Mr. McGregor. Mr. McGregor. There. Mr. McGregor popped a sieve on the top of Peter. But I don't remember that happening in the story. Peter escaped the garden, yeah? So did that really happen? I must query a bit more about this pop because that concerns me. So let's go through and have a look at the pop. So I'm querying my pop. This is a very efficient query system, obviously. Here's my pop. Now Mr. McGregor intended to pop the sieve upon Peter. So maybe he actually didn't do that. So this is allowing me to collect lots and lots of semantic information from text. It's allowing me to code this in a way that I can read. It's also allowing me to code this information in a way that I can easily query. It's also allowing me to code this information in a way that's easy to compare with what other people might have done. Because I've got this data log coding. The data log coding has no variables. Variables have been kind of got rid of, and just has the links back to the natural language. So that's really quite strong, I think. I have a few more minutes, yeah?
3 more minutes.
Oh, good. This will lead me to my latest obsession is to look at esoteric languages. I'm looking at Sugari Ben is not so esoteric. It's a live language being spoken, and we're busy annotating a Sugari Ben corpus. And one of the things we want to do is give it very rich semantic content, and that's a problem because I don't know any Sugari Ben, and my students don't know any of this theory. So how do we match that? And the answer is these graphs. So yeah, I should have time to just quickly mention that. I had other things I could have mentioned, but this is mildly appealing. Oh, I need to find the data there. So this is the Sugari Ben pars corpus, and here's a nice sentence. So the English because it and this is a child was a child. They, and the they is the old man and the old woman, got from the snow woman. It, the child, must have melted when she, the old woman, put the child into hot water. This is like Albury, lots of snow and snow creatures and stuff. And this is the Sugari Ben, which we've annotated, and we've kind of put in traces and pros and connections and all of that. And also at the same time I've got this English. Now this is not an English. Yeah, it's hard to know what the status of this is. This is more. So this is real English in the sense that it's grammatically makes sense, but it's trying to capture the dependencies and replicate the dependencies in the Sugari Ben. And this is the way that we can. This is the way that I can communicate with my students to really capture with quite a lot of confidence the semantic representations that are actually in the Sugari Ben. So this is English liberally created to replicate the Sugari Ben connections. And how can we check that? Well, we can go to the graph layer. So here's the graph of so the English that I end up with is the translation that I read to you earlier. And when we go to the graph, we end up with this graph, and that's what that graph looks like. So this is in the way. Sorry. And so if you can keep this image of connections in your mind, and we switch over to the Sugari Ben data, which I don't know how to get rid of this horrible thing. Yes, not the. We should see that we're getting exactly the same dependencies replicated. So the same connections. So this Z here is a zero pronoun in the data corresponding to the mother and father, and this is a zero pronoun corresponding to the old woman who puts the poor child into the boiling water and melts away. So so this is giving me a very nice way of annotating really quite difficult stuff otherwise, and having very tiny granular decisions about dependencies and relationships. And we're also doing this for old Japanese as well. So at some point there'll be a nice old Japanese version that has all of these kind of styles of connections, and this very useful translation that's not only being useful to understand what the sentence means, but also understanding how it's been analyzed for a layperson. So this is about making our analysis really accessible to understand that these connections really are of significance and really matter. Thanks. I guess I should stop here.
Now we are of course interested in
how he analyzes Peter Rabbit and Harry Potter when told in Sugar dialect. Any question?
Thank you for your talk. I would like to know how you analyze relative clauses, especially with relation to quantifiers. For example, like every boy who has a bicycle is happy. Like every boy who has a bicycle. I think there could be some problems with representing the scope, how you put the verb into the scope of the quantifier.
I don't think so. It's no problem.
Okay.
But we should see. You want a relative clause, yeah? So I might as well find a relative clause that's kind of already analyzed rather than try and do something off the hoof. And it needs to have every. So there probably aren't that many in the book there. Yeah. Maybe I'm in no position to think about this. Every man. Oh, I have. Yeah. Oh, yeah. Okay. Well, I mean, the very first one. Everyone who's working flat out is already a relative clause. Oh, literally everyone who was on the conference call would have been. Yeah. This is nice. Okay, so this is the kind of the thing that you're talking about, yeah. So how are we getting a semantic representation from that? So here we have the semantic representation. So we've got everyone that's introducing a restriction, and so that's everyone literally on the conference call. And then this is the nuclear scope would have been able to see behind me.
But how you make sure that the was is in the scope of the quantifier? It's
how? Because it links via this guy.
But it's linked from the top, not from the bottom.
No. Well, I mean, it's linked through a restriction line. Yeah. So I can factor.
I mean, what about this one? Is it in the scope of the restriction?
Yeah, this is also in the scope of restriction.
But what about this one?
Is not in the scope of restriction. Because this is divided. Yeah?
But how is the difference?
Because this inherits restriction and this inherits scope, and scope will gazump restriction because of accessibility. Yeah. Yes.
That's because they become parallels. These are the same.
Yeah, clear, because this is the subject for both the internal relative clause and the main clause. Yeah. But we can separate out the content of the restriction from the content of the scope because we have the path information. So the path information is telling us, and okay, from the graph, you have to interpret the graph in a particular way, and we can interpret the graph with a bias that tells us that stuff that's here is accessible under universal quantification, and stuff here is obtainable from that location because of the scope path information. So this is a nice way of representing scope, even within a graph setting.
Thank you very much. So I have practical questions. You give an estimate of how long it took to annotate all of that data? That looks very, very nice. But
yeah,
in terms of
10 years.
10 years. But okay, and there an annotation guide that
Yes, there is. There is
There is, okay.
there's a book, annotation book. Yeah, like
10 years?
200, 300 pages.
And also, is there a way to go back to the original text in the system?
Oh yes, of course. Yeah.
Oh.
Yeah. I mean, the whole point is to be able
Yeah.
to very easily fit back to the original, so that we can check out that what we're doing is really tied to the original.
Final question. The English version of the non-English language,
Yes.
his name I forgot, was
Suraru dialect.
it was automatically generated? Or
No, it's
no,
hand
okay, but
annotated.
did you consider using those semantic representations to generate the text?
In the
So the way to
Oh yeah.
automatic
So
translation.
in previous work, I have played around with generation from these things. Yeah, and you can do a really good job at generating from these things. Yeah, because they contain so much syntactic information.
Yeah. So
Actually, that's a kind of supplementary thing. It's a exercise I give to my students. I give them these graph representations, and they have to reconstruct the original sentence. And this is very nice because the very words of Japanese that are missing from these graphs, like relative pronouns and determiners and complementizers, are the very things that they need to fill in order to make a grammatical sentence. So it's really highlighting. It's useful as an educational tool as well.
thank you very much.
I think that would be some kind of TA works.
Okay, so have you analyzed the conversation data rather than like a single?
Oh yeah, the corpus includes conversation.
Conversation, like between A and B.
Correct. Yeah, there's conversational data within the corpus. The corpus is data from various sources, and we have a large slice of spoken data from the BNC, British National Corpus, that has interaction.
Then, yeah, so I have a question for the semantics of conversation, like in the semantic representation.
Yes.
There is a question and a discussion, one question, and then
Yes.
conversation moves according to.
Yeah. That kind of that richness of semantic representation isn't trying to capture that. I mean, there's no reason why you shouldn't extend that to that scenario, but incidentally, I should say, I mean, it's still working for English. It's also working for Japanese as well. I mean, the 10 years wasn't spent exclusively on this corpus. That's like a hobby. The real work I've been doing for 10 years is building a Japanese corpus, and this style of semantic representation and dependencies that is available through that for this with the same reasons. This is a language-independent style of treating stuff.
Okay, could you make it short question? Very short.
Oh.
Thank you for so my first question is what do you think about auto generating these graph semantic representation using some recent techniques like order embedding and transformers?
Yeah, I mean, but the data set is on the web, so if you want to do that work, I'd love to hear the result. I'm personally not interested in contaminating myself with that technology because I think it will. I want to, I'm a purist. I want to do this by hand because I think I'm getting I'm not being contaminated by the biases that are embedded in these models. But I'd be very happy if people took this data and played around with it in whatever way they want. I mean, there is now 500,000 words of English, so that's a sizable data. There's 1.5 million words of Japanese, which is even more data. One of the main annotators I see.
I want to move your GitHub pages.
So let's name the speakers once again.